Hello, everyone, and welcome to today's webinar on superconductors for power transmission beyond the age of copper. My name is Leila Sawyer. I'm the Secretary General of Current, and I'll be moderating today's webinar. So before we start, maybe just a few words about Current. We are the voice of innovative grid technologies in Europe, a fairly new association, now 11 companies, all working together on technologies that will help us make the most out of our existing electricity grids and build new grids in the most efficient way possible. And yeah, this is a very important moment in time for us. All around us, we see the ambitions for renewables are growing by an order of magnitude, and it is clear that this needs to go hand in hand with powerful electricity networks. And if we look at what, as a society, we're going to be asking of our electricity grid by 2030, 40, 50, it is clear that innovative technologies will be very much needed. So this brings us to our topic of today, superconductors for power transmission. To some, this may sound like something way off into the future, but we are here to tell you that there is a lot being done on the ground already, and a lot of plans are being made for the very near future. So we have a great lineup of speakers for today, but before I introduce you to our first speaker, a few household messages. So today's webinar is being recorded and will be made available along with the slides. And if you have questions for our speakers, please put your questions in the Q&A section, and we will try to get them to them in the panel discussion. So now for our first speaker today, we have Dr. Owen Hodge, Chief Engineer at Supernode, who is going to introduce us to the principles of superconductivity. So Owen, the floor is yours.
Thanks, Leila. Very happy to be here. So as Leila says, I'm from a company called Supernode. We're a member of Current. In fact, we're a founding member of Current. And today I'll speak to you on the merits of superconductors and more explicitly superconducting cable systems, which we believe will be a key enabling technology to deliver on decarbonization of our energy systems. Right, so firstly, our vision in Supernode. So we believe that people should have access to secure, affordable, and renewable energy. So we believe in decarbonization. We believe that electrification is the key vector to deliver on that. And in Supernode, we're developing transformative transmission technology based on superconductors, so superconducting cable systems that can carry vast amounts of energy over long distances in point-to-point connections or in interconnected grids, and they will allow us harness the volume of renewables that we need to deliver on decarbonization. Okay, so why do we need a new transmission technology in Europe? So as I say, we see electrification as the key vector to deliver on decarbonization, and we expect that electrical demand will triple by 2050. The nature of supplying that demand then, as you'd expect from renewables, is that we'll have a lot of solar and a lot of wind. So we expect more than 800 gigawatts of solar to be brought on stream in that time frame, and more than 450 gigawatts of offshore wind to be brought on stream. To put that into perspective, currently we're sitting in and around 20 gigawatts of offshore wind currently installed in Europe. So a massive change needs to be undertaken to deliver on the volume of renewables we need to decarbonize. The nature then of a system where the energy sources are renewable is such that they're located at the periphery of the continent. And the nature of that is that we then have to translate high capacities of power over long distances. So we're moving away from the old energy paradigm where we could co-locate power stations with our population centers and our demand centers to one where vast capacities of energy source are located remotely from where we need it to be. And the reality is that current grid technology simply cannot deliver decarbonisation in this way. So copper is limited in terms of its efficiency, it's limited in terms of its cost, and it's limited in terms of its capacity. So we simply don't have sufficient transmission capacity within Europe to deliver on a decarbonised system. And we need to innovate, and we need to invest in innovation and in transformative technologies, such as those of superconducting cable systems, to deliver on decarbonisation in Europe. Next slide, please. Okay, so just to look at that graphically, as you'd expect, the best wind resources available in the north of the continent, so in the North Sea and out west, out in the Atlantic, beyond the north of the UK and Ireland, off the coast of France, etc. And the best solar resources available in the south of the continent. And the population density then is dispersed around the continent and with large population centres towards the centre. So the new paradigm is that we need to move vast amounts of energy from both the north and the south into the centre of Europe. And to do that, we need a new type of transmission grid. Next slide, please. So we advocate for a super grid, essentially, or a meshed pan-European grid to deliver on a system that's based on renewable sources. So we understand that the solar and the wind can be intermittent, and they're inversely correlated. So in the summer season, we've got really good solar resource in the south, and in the winter season, we've really good wind resource in the north. And we need a grid that can transmit that power from those sources to the population centres. So we've done some studies within Supernote with academic partners on the totex of a pan-European interconnected grid. And what we found is that a significant cost saving can be achieved if that's planned for and implemented in a strategic way that overcomes the approach that we currently have around Europe, where essentially transmission grids are based around national borders. So they start and end at national borders with some amount of interconnectivity. That's the business as usual approach. And we think going forward to deliver on decarbonisation, that's not going to serve us well, and we need a new approach. Next, please. Okay, so looking around the world to see how this long distance high capacity transmission is being handled by other countries. So we're using China here as an example. We could use the United States also. They have the luxury of addressing high capacity long distance transmission through overhead lines that we just don't have in Europe. So what we're showing here is a phenomenal engineering feat. So it's a 12 gigawatt connection line from the hydro resource in the northwest of China down to Shanghai and Beijing, where the population centers are. And that's being handled through this overhead line that we've seen here. This simply cannot be achieved in Europe. There's no public acceptance for overhead electrical infrastructure. The future for Europe is cable technology. It's DC cable technology. And to realize that most effectively, we think those cables need to be superconductor based. Slide, please. So what are superconductors? So most of you will know superconductors are materials that offer zero electrical losses when certain criticalities are met, primarily that they're kept cool. So superconductors are more efficient than conventional copper cables as a result. Because they suffer no losses, they have no dual heating, they can be operated at much higher power densities than copper cables. As a result of that, they can be operated at much lower voltages. So we increase the current density and we reduce the voltage levels. And essentially, we can operate at transmission levels of power capacity at distribution voltage levels. So this is really, really advantageous. Voltage in electrical equipment drives size, and that drives cost. So if we have a system that's based around a lower voltage cable technology, we can realize significant system cost savings, and that can be achieved through superconductivity. I guess to compare directly to copper, and it depends on application and design, etc. But we like to propose that there's a ratio in terms of current density of 1 to 200. So in terms of cross section, one of the tapes that you see on the screen per millimeter square can be 200 times smaller than that of copper. So that is obviously very advantageous in terms of the size of the cables and the leeway and consenting and all that type of challenge that exists when high capacity copper needs to be integrated in the system. So we're very confident that when we look back in 20 years, we'll confirm that superconductivity has done for power transmission what fiber optics have done for telecom and the twisted copper pair. So next slide, please. Just to give you a quick overview of some of the projects that are currently operational. So generally the applications to date in terms of cables have been distribution level, and the commercial value proposition for those applications is that of urban congestion or urban density. So essentially it comes back to that mantra that you can pack transmission level capacities into distribution level voltages, and in an urban setting that's advantageous because you've got smaller leeways for cables and reduced footprint infrastructure either side. So the flagship project in Europe has been the Opacity Project in Essen in Germany. This is a 1 kilometer project, 40 MVA and 10 kV. A similar enough application is a project in Shingle and Seoul, operated by KEPCO, the Korean TSO, since 2019. Again, 50 MVA, 23 kV. And I think Mike Ross is online from AMSC, and he'll provide some further detail on the REG project in Chicago, which came on stream last year. And then interestingly, from a transmission perspective, are the Horizons project and the Munich project. So the Horizons Best Path projects demonstrated a high capacity, high voltage superconducting cable system, so 3.2 gigawatts and 320 kV. And the SuperLink project, which is currently in its first phase in Munich, signals a step change in the acceptability of the technology from regulators. It's a 12-kilometer long project under the city of Munich. Capacity rating is 500 MVA and 110 kV. So we expect that project to be delivered by 2027. So phase 1 is out to the end of next year, and then phase 2 out to 2027 when the project should come on stream. Next slide, please. Okay, just to recap on some of the key advantages. So superconductors are the most efficient way of high capacity bulk power transfer. They're particularly suitable for underground technology. They're smaller, they're more compact, they have greater public acceptability. A key advantage of systems based on superconductivity is that they can operate at lower voltages. This reduces size, which reduces cost, and reduces consenting risk, which, as we all know, in the electrical space, can be a significant challenge to overcome. So the applications that we see then in Supernode, the first of those is that of urban congestion. So that's the application that we see being addressed through the distribution level projects that are currently operational. So as I say again, the key advantage there being that we can transmit transmission level capacities at distribution level voltages, so much more compact and easier to integrate in urban dense environments. The next application is direct connections of large scale offshore renewables. So we see this in Supernode as an early application of our technology. So these are point-to-point connections for offshore wind farms, for example. And then the third application is grid reinforcement at scale. So this is a meshed pan-European interconnected grid that we think can only be delivered through superconductivity, and which we need for us to realize the potential benefits of a system that's based on renewables, which is essentially a weather-based system, which just allows us to overcome the intermittency in that system. Next slide, please. So just a few slides there, just to give you a quick overview as to what we're actually doing in Supernode. So we're a technology development company. We're developing superconducting cable systems. They're high capacity systems, so MVDC, 2 gigawatt plus, long distance transmission systems. We're developing a cable system for both the offshore and terrestrial applications. From an engineering perspective or technology development perspective, we're very much focused on novel materials development and novel approaches to thermal management, which will allow us leverage the maturity in superconducting cable systems that exists today, and then translate that into higher capacity and longer distance transmission systems. Next slide, please. So just to give you a quick overview of our timeline then, Supernode was founded in 2019. In 2020, we achieved a statement of feasibility from DNVGL, which is a third-party endorsement of the technical feasibility of our technology concept. and we undertook some benchmark testing for an early generation of our cryostat technology. Last year then, we applied for patents for key subsystems of our cable technology, and we undertook proof of concept testing on those systems. This year then, quite recently actually, we moved into our own technology centre in Dublin, and we've progressed the technology development through the technology readiness level from 3 to 4. That work is ongoing into next year. That's essentially laboratory testing in our tech centre in Dublin. And then in the medium term, our objective by 2025 is to deliver a system prototype which will validate the key functionality of the system and which will validate the techno-economic assumptions that underpin the commercial value proposition of our technology. So I think the last slide then. So just a quick overview of some academic studies that we've done with our partners in Strathclyde on integration of our cable technology. So the first paper is a point-to-point study, operational study done on integration of our high-capacity cable system, where we've put the system through various operational modes and determined that there's a key advantage in terms of fault protection to be accrued through HCS cable systems. The next study, a translation of the first one, an extension of the first one into meshed grids, has been approved for publication quite recently in the IEEE Journal on Power Transactions. So we looked at the operational advantages of a meshed DC grid comprising our superconducting cable technology, and essentially found similar benefits could be accrued. So a key benefit is that of fault protection and of power dispatch management when there is a fault on the system. Okay, I realize we're pushing for time, so I'm happy to wrap it up there.
Thank you. Thank you, Owen. Thank you for that very broad overview and presenting also the work of Supernode. So indeed, for the sake of time, I suggest we move on to our next speaker, Dr. Matthias Noe, a professor for energy applications of high temperature superconductivity at the Karlsruhe Institute of Technology. And he will be talking to us about applications of superconductors in the power system and fault current limiters specifically. So thank you, Matthias, the floor is yours.
Thank you, Laila, for the introduction and the invitation, and a warm welcome also from my side. If we can continue, please. Yes. Before we continue with the cables, I want to shortly introduce the opportunities for superconducting fault current limiters. And the next slide, please. I expect some people are not very familiar with that, so that I shortly explain what it is. The superconductor has a very nonlinear current voltage curve that you see here on the left side. When you exceed the current, resistance develops, and this is intrinsic just by exceeding the current. And this is what we use in the short circuit that you see here on that side. Here is the superconductor in the middle, and you can put any impedance in parallel to adjust the currents according to the specification. And this results, next slide please. This results in the main features of a fast short circuit limitation. Within the first current rise, we have no impedance and normal operation. We have a fast and automatic recovery if the circuit breaker opens for some time. It is fail-safe, which means that even if the superconductor fails here in the middle, you limit the current anyway, and you protect your equipment. And it is applicable, as you see in a minute, at high voltages and in some cases already cost effective. Next slide, please. This is a typical short circuit limitation. In normal operation, you just see the normal current and nothing else. And within the first rise, the resistance limits the current to a specified fault duration. Then you need some recovery time, but the recovery time can also be 0. and then you start with normal operation again. So there's no conventional device that can have the same features here. That's the nice message for a fault current limiter with superconductors. Next slide, please. What are now the opportunities in transmission grids and high voltage grids? Yeah, you see here the rise of the short circuit currents at different substations of a distribution system operator in Germany, with the different years, and in the red limits, in the red bars, you see the limits of the substations, typically 40 kiloamps, and you see some of them, some substations already exceed shortly the 40 kiloamps. This means with the fast rise in the short circuit current, sooner or later you have to upgrade the system, and in some cases you have to build completely new substations, just because of the rise of the short circuit current. And this is not only true for a specific distribution system operator. If you put on the next slide, this is also for the transmission system operators in Germany. And you know, 63 kiloamps is quite a limit for circuit breakers, and in some places and in more places you come very close to that limit. And you see also the very fast rise in the short circuit current. So you have to do something, and of course you would think that the deactivation of coal and gas power stations would reduce short circuit currents. But as you see on the next slide, there is quite a big extension of the grid, not only in Germany. You see here the example in Germany, but also in whole Europe, as Jon mentioned before. And this comes up with a large investment of more than 80 billion euros by 2035. And you see here the numbers, and these are numbers from last year. In Germany, we increased these numbers just recently. So there's a huge effort to upgrade the electrical grid, and this will reduce the impedance because of a higher meshing, and this will increase the short circuit currents. If we go to the next slide, please, we see a typical specification. Here's an example in 110 kilovolt grid or 380 kilovolt grid. You have to handle several kiloamps. You have to reduce the short circuit current drastically, and you have to handle different fault durations, of 250 milliseconds, for example, or even with fault right-through conditions in 110 kilovolt. And if you go to the next slide, we have recently finished, together with a company, feasibility study, a detailed feasibility study on 110 kilowatt limiters, and we are now in the middle of a new study for 380 kilowatt current limiter, and that's why we have estimated the amount of superconductor and the cryostat dimensions, and of course we are working on the economic feasibility as well. You see, in general, this is doable. And as you see at the next slide, which comes now to the end of my presentation, my short introduction here, 220 kilovolt have already been realized in Russia by company Supercox, installed in 2019 and still running in a permanent installation with a few other installations coming up very soon. So this is also from the technical point of view, the first prototype at high voltages, 220 kilovolt, and in the next slide you see at medium voltages and also at high voltages, several prototypes have been realized. They are in the grid already, and some of them are still running. Very reliable. We have heard of no reports on damages of these current limiters. They usually use YBCO tapes, and even a few companies like LS in Korea or Supercox in Russia started to offer commercial systems. With this, I would like to finish my short excursion to superconducting fault current limiters, And to summarize, the resistive type superconducting fault current limits are definitely technically feasible up to 220 kilovolts and above. Upgrading this to 380 kilovolts and higher currents is an engineer's effort and possible, and the economic feasibility needs more detailed design studies. That's all for this short introduction. I would like to thank you very much for your attention.
Thank you, Matthias, for that very informative presentation and the promising technology for voltage fault limiters. So I would now like to introduce Mike Ross, Managing Director of American Superconductors, AMSC, who will be sharing his experience with their project in Chicago. So thank you very much, Mike, for being here with us today.
Yeah, thank you for the opportunity to speak to this group. Really appreciate it. So what I'm here to talk to today is about AMSC, or American Superconductors project in Chicago. We're really focused on the aspect of decarbonization of the system, where we have to think about when all of these electric vehicles, when all of the space heating and the cooking of food, when all of those things are brought away from fossil fuels to electricity, not only are we going to see a lot of increase in capacity requirements in a lot of requirements for the grid for getting more power into cities, but also there's more of a reliance on the grid. We're going to be dependent on the grid for transportation, for space heating, for cooking our food. And so reliability and resiliency is going to become critical. Next slide, please. So our project in Chicago is an application of superconductor cables that we at AMSC refer to as the resilient electric grid, or REG networks, which is a way of using superconductor cables, one application of superconductor cables that really focuses on increasing reliability while dealing with the other challenges and the other realities of doing major infrastructure projects in dense urban areas. So this technology allows us to do things that you just simply can't do with copper or aluminum cables, and to try to avoid the challenges in urban areas, like increasing the size of substations and right-of-ways, and avoiding using oil-filled cables and gas-filled cables and so on. So we're trying to increase reliability while at the same time making it more feasible to do infrastructure projects in urban areas. Next slide, please. So as some of the other speakers have talked about a bit about the advantages of superconductor technologies, really the key advantages for the application of reliability and resiliency are the fault current limiting characteristics of cables that the previous presentation discussed in details. So not only is that fault current capability, limiting capability built into standalone fault current limiters that Professor Noe was talking about, but it also is built into our cables. And that characteristic is really critical for some of the applications. Also important is that we can move a large amount of power in a very, very small space. And that in turn makes siting, permitting, installation of the cables much, much easier. Next slide, please. So the key application in urban areas and what we call our REG applications of superconductor cables are mainly focused on interconnecting existing substations together at the distribution side. So distribution voltage levels, 13.8 kV, 11 kV, 33 kV, and so on, so that we can move power from substation to substation independent of the transmission network and the transformers associated with that. And what that means is that if we can loop substations together in a ring, like we see here at the distribution side, we can move power from substation to substation, even if there's a problem occurring on the transmission system or on during the loss of transformers and things like that. So generally, what we're using superconductor cables to do here is create a backup system to the existing transmission grid which then allows for higher reliability and higher resilience. Next slide, please. So specifically, the project in Chicago, the goal is to interconnect a number of substations in the downtown Chicago area to increase the reliability and resiliency of those cables, of those substations. And what makes it important for the specific project is that in downtown Chicago, there are two substations that are fed radially. So they're fed from one source at 69 kV. And then a third substation that's connected by multiple sources at 138 kV. And the goal is to interconnect all three of these substations together so that if you have a problem with the transmission to any one substation, we can move power through the superconductor cables and keep the lights on during those events. And that in turn increases the overall reliability of the network. And we want to do all of that without installing a lot of high voltage transformers, a lot of infrastructure, or require any land acquisition or substation expansion. And so what we're going to see is how we can do that with superconductor cables. Next slide, please. So ultimately, this is the project that we will eventually perform, ideally in Chicago. As you can see here, there are two substations, A and B, in the northern loop of the downtown Chicago area. Those are served radially from one source, which means that the reliability of those are relatively low compared to many urban substations where you have typically multiple sources to a substation. And that creates some challenges. And of course, it's easy to say, well, let's just build some more transmission and make these stations more reliable. But the reality is that's a very, very difficult thing to do in dense urban areas and extremely expensive to do using conventional methods. But if we use superconductor cables at distribution voltage levels, but very, very high capacity because of the characteristics of superconductors, we can interconnect these substations together so that if there is a problem at one, we can move power among the substations and again, keep the lights on. Next slide, please. The project that we have executed and has been energized and operating since August of last year, coming up on our 1-year anniversary here, is a smaller scale project so that the ComEd, the electric utility in Chicago, could get a bit of experience with the technology. It is a smaller scale project, but it is doing exactly the same thing that we saw in the previous slide, just a little bit smaller scale so everyone can get a bit more comfortable with the technology. So the next slide will show that project. So within this one fenced area in northern Chicago, there are two substations. So thinking of the downtown area where there are 3 separate substations serving that portion, in this one fenced area, there are 2 substations, one on the north side or the top right-hand side and one on the bottom left-hand side. And so what we've done is we've taken a superconductor cable at 12 kV and we've interconnected the 2 substations in this one fenced area together so that in the event that you have that they have a problem on one side or the other, they can rely on the superconductor cable to move power across. And your first thought might be that, well, that they may not use this cable very often because how often do you have transmission outages and transformer outages? And the reality is that they use it quite a bit because there's constantly maintenance being done on equipment. And it's one thing that people don't often understand about power systems is that all these components need to be maintained. And so when you take a piece of equipment offline to maintain it, your system's at a little bit more risk that if something goes wrong during that maintenance period, you may have a situation where you have to drop load. And so what this cable does is it's used quite often when ComEd is doing maintenance at this and nearby substations. Next slide, please. Just some slides showing the installation. This was the project being installed. These cable reels that the superconductor cable were delivered on are standard sized cable reels that are used widely in the industry. The actual installation of the equipment was done by a crew that typically works on conventional copper cables. The equipment used The actual people used are the same sort of folks and equipment that are used in conventional equipment. And this cable is actually installed using 100% union labor. Next slide, please. Here is one end of the cable. So the termination of the superconductor cable is in the center of the screen, and that's connected to those three black bars. Those three black bars are conventional copper bus bar, rigid bus bar. So that's what needs to you need to use in order to move the same kind of power that the superconductor cable can move conventionally. So those three rigid 4-inch diameter copper bus bars are able to move the same amount of power as our cable that you see in the bottom left-hand portion of the foreground, where that cable can be put underground, it can be pulled through ducts, it's very lightweight, it's bendable, and all of those things that you need to be able to go from substation to substation. You can't do that with rigid 4-inch copper bus. It's just not practical. But with superconductor cables, we can. Next slide, please. This is the other end of the installation. So this is a more conventional way that a termination would be installed. This is done outdoors, but you need to envision what this would look like indoors. The termination itself would be in a metal-clad switchgear cubicle inside a building. The cable would come in from the substation, go through the basement, and then into the termination. And then this would ultimately look like any other piece of utility equipment in a substation. Final slide, please. And then just to get the point across here of what we're trying to do, in that little termination on the left-hand side, you can see the picture with the green circle. That little termination, which would be inside a switchgear cubicle, delivers the same amount of power as a transmission, 138 kV transmission line with all of its switchgear and transformer and so on. So the idea of this slide is to show how much power we can deliver using this technology in a much, much smaller space, which is absolutely critical for the applications we want to do. Thank you.
Thanks a lot, Mike, for sharing all that information on your project in Chicago, and look forward to hearing how it develops further. Now I would like to introduce Doug Villen, Principal R&D Engineer at NKT, who will tell us about his project, the SuperLink project.
Yes, thanks a lot for this invitation and the opportunity to present our work at NKT on superconductors. I'm sitting here on a reasonably weak Wi-Fi connection, so I will at some point close my video while I'm talking. On this first slide, you can see myself at the site of a project we did some time back together with American Superconductor and Mike Ross company back in Columbus, Ohio, where we demonstrated the first HTS triax cable that was running for 6 years in the grid of AEP, American Electric Power. So next slide, please. NKT then is focusing on this solution of the urban congestion problem that previous speakers were mentioning. We see urbanization as a driving force, the increased use of electricity, e-mobility, of course, higher energy densities, and replacing old cables, and not the least renewable power sources that replace old power sources. And you may not know or believe the incredible density of existing hardware installed in the world's large cities. So there is, in many cases, no footprint left. And with footprint, what we see is the geometrical footprint, so just physical space. Our installers often have to really crawl underneath and build caverns in order to join cables underneath existing infrastructure. But also thermally, when conventional cables run in the streets, they can get hot as 60 or 70 or even 90 degrees Celsius. That derates and can affect other equipment. So with this new superconducting technology, we hope to develop really attractive solutions to solve some of these issues. Next slide, please. We are focusing on two kinds of products. So the first one that I mentioned on the opening slide is the HDS Triax energy and fault current limiting cables. And they have been developed primarily with partners in the USA. And they're suitable for the 10 to 72 kilovolt operation area. And we have demonstrated 3,000 and 4,000 amp versions of this technology. And we think it's suitable for between 1,000 and 5,000 amps. So that brings powers of 25 to 500 megawatt. So it's truly transmission level power at distribution level service. So this is a commercial offering that we can provide today. The drawback of this product is the price level. Because of the advanced technology, even if we have matured it over the years, it's still relatively expensive. So compared to more conventional medium voltage equipment. So today we're focusing 100% on in our development efforts to bring an attractive solution at the high voltage area. So we have selected this design where we do 3 single phases in a common cryostat. And we believe that we will reach the highest efficiency and the best economy in this way, even if there are alternative designs. What's very interesting is that we can use exactly the same materials, the same machines, and the same manufacturing processes for both these product groups where we would normally have completely separate factories built for these different voltage levels. So the high voltage version here we're demonstrating in this SuperLink project together with the Munich utilities and a bunch of partners I will present here. We expect this to come into operation at 2023 with a longer length than at a later date. Next slide, please. The partners in this Stadtwerke Munich SuperLink projects, not the least the funding agency Bundesministerium für Wirtschaft und Energie, which have a really long-term vision for energy restructuring. And they're investing heavily in this technology by supporting this project and several other projects. The customer for the project is Stadtwerke Munich, Stadtwerke München, who operates the electric, gas, and I think also the bus system in Munich. We have NKT. Teva is the wire manufacturer in this project, and they have a unique process to bring up very high performance tapes at, I think, really cutting edge price level today. Then as the partner for the cooling system is Linde, whom all of you know. It's an old and established and very large company with an extreme high level of experience, firstly in advanced cooling technologies, but also surveillance technologies. And they have surveillance centers around the world that can operate cooling equipment. We have academic support then from Fachhochschule Südwestfalen, who's doing some studies for us on the insulating materials. And not the least, Matthias Noe's, Professor Matthias Noe's department at the Karlsruhe Institute of Technology, who has probably one of the world's longest standing and highest level experiences of high temperature superconducting applications and the science behind it. So that is a fantastic team that where we get very good support to bring this one step further. Next slide, please. So the task at hand here is a very concrete case where the end customer sees a big benefit of connecting an existing substation at the south of Munich to the high voltage overhead line at the north of the study of Munich. Several detailed studies have been done of the various alternatives, and the outcome of these studies have shown that HTS could for real be a very good alternative. It's a limited distance, so only about 12 kilometers. It goes through a landscape of very densely populated city area. The available space is essentially under the sidewalks of the streets in Munich. So the task is to stay underneath these sidewalks. There's very limited possibility of using other routes, and the alternative of tunneling underneath a big city is exorbitantly expensive. So we're looking at 500 megawatts at operation voltage of 110. So one single HTS cable then replaces 5 conventional cables, which would require 5 separate routes and through the center. So next slide, please. The criteria that we must provide, and which are not easy at this stage of the technology, is to really save space. So no big equipment. There's very limited room for construction. To get acceptance from the public and the customer by providing something with very little electromagnetic fields around it. Essentially no ground heating, and very limited size and duration of building sites during the course of the project. We all know what it's like when the whole city center where we live gets dug up and resulting in traffic congestion and such. We also need to provide an economic solution in terms of cost of building and operating this system for 40 years. And we need to show that it's sufficiently technically mature, because electric networks are really critical infrastructures that a lot of people depend on. We need to deliver at least 500 megawatts in the future. It could be more. And we need, it's not enough that it's superconducting and that it does a job. To be acceptable and adopted, it also has to show energy efficiency, because the whole industry is striving towards a greener future. So we need to show energy efficiency. Next slide, please. So the cable system, as I described, we have an annulus here in the cable of liquid nitrogen, which is also serving to impregnate the cable, and it replaces then medium like oil or SF6. Liquid nitrogen is a perfectly environmentally compatible substance, so there are no pollution issues there. We're developing this particular cable design. It's not necessarily novel, but we still think it's the best design. And we're striving to make this high performing and ultra compact. Next slide, please. Together with Linde, then, we're also focusing on this distributed cooling system. We believe that with today's technology and in a compact system, we need to have intermediate cooling stations at spaces of around 3 to 5 kilometers and at the ends of each system. And the customer is clear about the fewer cooling systems, the better along the way. On the other hand, they also want an as compact system as possible. So the optimal point here, we think, is 1 or 2 intermediate cooling stations. As a backup, liquid nitrogen can be trucked in, but the customer is very clear that the preference is a closed cooling system. Next slide, please. So where are we at in terms of time here? We started the project in 2020 in the fall, and we have performed most of the development tasks here last year, 2021. And this year we are in a phase of testing and demonstration. So the plan is to complete a type test for this 110 kilowatt level with an attractive product by the end of this year, and then start a field demo at a substation in Munich in 2023. And this will run for at least half a year or maybe up to a year in order to have a pre-qualification of all the components. And following this successful demonstration, then this solution will be commercially available from NKT and partners. Next slide, please. So in summary then, we think this could be a cornerstone and the longest installation of HTS cable systems. And it aims then to really prove the economically sound and technically smart solution for congested cities with a minimal environmental footprint and much less disturbing construction sites than what we're used to. It will create flexibility in growing networks and will increase the energy efficiency in urban distribution grids. And all in all, it would then minimize the impact on citizens, both during the construction phase, but also during the use phase over the life of the system. Thank you. Or next slide, maybe to show our nice slogan. We connect a greener world.
Thank you, Doug, for that presentation. We have heard now from various different technology companies, what they're working on, their innovation projects, etc. Now we move to Norela Konstantinescu from NSOE, Head of Section Innovation, to look at how our system operators looking at superconductor cables. How is NSOE, and what does that mean for 2050? So thank you, Norela, for speaking on to that.
Thank you very much, Laila, for this introduction. I was very pleased actually to hear the concrete examples which were shown before, so from different corners of the world. If we go to the next slide, I don't have too many slides, so only two, so I hope that I will also keep it short. From our perspective, and of course it's the association perspective, so I will not go in the examples which were shown previously. We have more examples, but I would like to make a kind of summary of the use or the view on the superconductivity. So it was mentioned that indeed this is the technology regarding the high temperature superconductivity, looking mainly at 110 kV. And the advantages of using this technology have been underlined by previous intervenants. Of course, this is important from a pan-European perspective, given the present conditions regarding the deployment of new infrastructure. I think we still need, of course, to have this deployment of new infrastructure, but this, of course, takes time. And technologies like what Laila, I think you mentioned in the beginning, the grid enhancing technologies can actually support those developments. Of course, the superconductivity maybe is not at the same level of maturity, like, for example, what you see here on the slide. So there are a lot of abbreviations, dynamic line rating, which is already in place and which can be deployed today, and it is deployed today. Or, for example, the static synchronous series compensators. So the superconductors are still a technology from our perspective, which has to be advanced. We were trying actually in our reference collection of technologies which are used by the transmission system operators into what we called Technopedia. So we have more than 65 technologies which are gathered in that reference. So it's available on the NTOE website. So we were trying to assess actually the technology readiness level, also from the perspective of the use by the transmission system operators, both in DC and AC systems. The advantages you mentioned indeed, so the high power carrying capacity, which indeed will allow actually to operate at voltage levels which can be reduced. Then allowing actually the facilitating of the bulk transfers of high capacity, and of course the reduction of the size and volumes of electrical equipment, which was I think underlined also by the images we saw in the example of from Chicago. The impact on the environment, this is also very obvious. It was said before, because of this compactness and higher capacity power transmission than the conventional cables, as well as the easier and shorter installation times, which actually would allow, and especially in urban areas, the routing into existing corridors like, I don't know, gas, oil, water, or even along the highways and railways. Therefore, this is a promising technology, but we would also like to underline the fact that probably we will need further developments. And I would mention that these developments, of course, are related to the urban areas. So we saw the examples today, but also to the offshore developments, which I think it was mentioned in the first presentation. Because they allow this large ampacity point-to-point connection and this transfer of quite high share of RES in the locations where it's needed. Of course, we have the energy efficiency, high energy efficiency in comparison with the HVDC, but we see that the superconductivity, because of still further developments which might be needed, as a kind of, how to say, tools which will develop, for example, for the offshore developments, together with the meshed offshore grids for bridging actually and for making the links between offshore grids, but also connection on the mainland and DC AC. I would like to mention in terms of future developments. So you see here some elements which are related to the technology itself, but from the transmission system operators point of view, we think that, of course, there is still the issue of having the reduction of the costs of the technology, then the performance, supply chains which might be needed to be put in place, and as well the monitoring system. In addition to the offshore developments which I mentioned, of course, the superconductivity can bring advantages probably in terms of interconnectivity between the different voltage levels, and also in space. So I would say that this probably will support the interconnectivity between TSOs and DSOs, but also at the level of interconnection. Regarding the future, so we actually identified the superconductivity as one of the potential game changer in work we do in NSOE regarding vision towards the low carbon energy system and economy, so zero, I would say. And there we see these developments which are related mainly to the urban deployment, but we also see this interconnectivity which can be achieved between, so complementarity which can be achieved between HVDC and superconductors for certain developments at the level of offshore. More information about this is going to come when we release this paper. It's a huge piece of work which we done there. If we can go to the next slide. In the period 10 to 12 October. And what we can say is that superconductivity probably it has a huge potential for development. From our perspective, there are these urban applications which are, as we saw in the examples today, are relevant. Potential developments can be related to offshore, especially in combination with the HVDC and what we called the supergrid offshore. So thank you for your attention. And apologizes for my voice.
Thank you very much, Norella. Really great to hear that NSOE and the system operators are also watching closely the developments by our colleagues in the superconducting area. So finally, last but not least, I would like to introduce Mario Dionisio, Policy Officer at DG Ener in the unit dealing with innovation, research, digitalization, and competitiveness. So thank you, Mario.
Yes, thank you, Laila. Thank you. And hello to everyone. Yes, I'm glad to be here in this meeting on superconductors, because new technology for the development of the grid. So this is just the introduction slide. We can go to the next one. A lot of things have been said already about the technology and well, the benefits and the superconductors. What is the policy context, or where we might need this new technology? You can see here the list of policy elements, the policy instruments that we are dealing with. So from the Paris Agreement, the COP21 to the next 27, with the national energy and climate plans, and the Green Deal, which is supported by Horizon Europe and other initiatives. This is the first part, let's say, kind of first part. If we go to the next slide, please. And this is what happened, other measures we put in place after 2021, since the pandemic. So with the Next Generation EU, so the response to the EU coronavirus. And after the 24th of February, Repower EU for the after the Russian invasion of Ukraine, yeah? So a plan to rapidly reduce dependence on Russian fossil fuels. Based on saving energy, diversifying supplies, and supporting our international partners, and accelerating the rollout of renewables. This is the part that mainly interests us here, and the other measures. We can go to the next slide, please. So among the initiatives, there are some, let's see, strategic ones, some really important ones. Someone has already been mentioned. One has been mentioned already. So it is the offshore renewable energy strategy with big development foreseen for the offshore 2030 and 2050. And in the same way now with the solar energy strategy, with a big increase in photovoltaic production by 2025 and also and beyond. There's also the new strategy on standardization, which is relevant. Why standardization? Because it is found as one of the main barriers for development of new technologies. So it is important setting standards in support of a resilient green and digital EU single market. And I would like to mention also the CHIPS Act for Europe. I think this is related to electronics, but yes, we're talking about electricity, but we know that electronics, and mainly power electronics, is more and more part of the electricity system. So this is why this is an important part, because until now, the main area addressed were, as we know, the automotive, health, building, industry sector, but now there's specifically the energy sector which is addressed, because the energy sector is a big user of electronics and power electronics. The next one, please. Next slide. Okay. So for the power network, with this big change on the production side, on how the system appears on distributed energy production and demand response and so on, it is clear that the business as usual to grid planning is not enough. We need something a bit more elaborated. So to go towards a modern energy system. So another point is the fact that with the renewables, we have a lot of the generation is interfaced with power electronics. So we need to deal with the grid more unstable, as more and more when the penetration of renewables will increase in time. So there is also to take this into account. And what we're discussing here also today is the fact that what big amount of so power current needs to pass through identified corridors. So we need some new technology replacing, or which can bring transport better electricity and conveniently and in a modern technological acceptable way. So this is related clearly to superconductors we're discussing here today. So the next slide, please. This is one thing. Clearly, we are in the research and development area. We're looking at a wide spectrum of technologies, clearly, which can be part of a modern energy system. And a wide part of these are object of discussion and also object of demos and RNI for energy. So it is a clear, also included the superconductivity. So superconductors is one of these technologies. The next one, please. Yes, I mean, this has been already said. We see what is the big difference. I took here some pictures, which shows clearly the difference from the normal transmission system to compared to superconducting. This is related to cables at CERN from the LEP, Large Electron Proton Collider, the traditional cables compared to the superconducting cables, the tiny one, which is a Large Hadron Collider. So there's a big difference. So it is useless that I mention what it is already known from what is the characteristics of the superconductivity. So they conduct better electricity when they are cooled. So this is the technology, but let's go ahead with the next slide. And here see some another image already that I've seen already in the previous presentation. So it shows clearly the advantages of reducing the space used by superconductors compared to traditional lines or cables. But clearly there are advantages, and but also we need a bit demos also on this, and also more research, because we mentioned until now high temperature cables. Low temperature, I don't know if it's needed. In any case, there's more research to do in this area. Next one, slide, please. So what the Commission is doing about RNI, and as I mentioned, in many innovative areas. So here in this timeline, we can see all the initiatives, so roundtable discussions with stakeholders that took place. And from these, we found out and we identified the needed areas where to increase efforts for research and development. And among these, we can see below in red, there's mentioned also superconducting transmission line, which was one of the latest calls in Horizon Europe. The next, please, next one. So concluding, I mean, it's clear we need to reduce global warming. This was the original, always the scope, the objective. So, but now we need to accelerate even more the RES deployment, so to reduce energy dependency. For this, EU policy instruments are put in place. So just to enable the decarbonization and the energy system and our economy. So it is clear that with the Horizon Europe, other EU funding instruments, we support this transformation, and we support also demonstration projects which are needed for to arrive to this innovation, to these findings, and go on with the energy transition. More RNI is needed clearly to obtain solutions applicable, because we're talking about energy system, and clearly we need to be sure that the technologies are working. And to do this, we need yes, more demos. I think this is the last one. So I just, yeah, please, in the next slide, I put here some useful links. And yeah, there are some slides presenting the past call, but these are not needed. Thank you.
Thank you. Thank you very much, Mario, for this overview and review of the Commission. And it's really great to hear that the Commission is monitoring closely what is going on in the superconductor industry. I would like to invite all our panelists to turn their camera on. We have already had some questions in the chat. Yeah, so welcome back to all of our speakers. I think first Mike would like to say something still.
Hey, thank you so much, Lana.
Yeah.
I neglected to mention our key European partners in our project in Chicago. Nexans of France was a critical partner for the supply and provision and design work on the cable, the terminations, the joints, and the installation of those terminations and joints. So without them, the project would not have been successful. I believe a lot of the work came out of Germany. And I believe the manufacturing of the cable was actually done out of Halden, Norway. Also, Sterling Cryogenics provided the cooling system, and they are based in the Netherlands. So without those key European partners on the project, there's no chance our project would have been successful. Thank you for the opportunity to think that.
Well, and that's, I think, clear from this presentation that we all need to work together on this. So we have some technology companies here. We have the Commission, we have NTOE. So maybe from the technology companies, what do you see as where policymakers could do more to support this, the development of this technology? Or what do you see is what policy could help with? So who, someone would like to comment on that?
Jump in there.
Yes, thank you, Owen.
So I guess what we'd like to see in Supernode is a mindset change, really, from the perspective that renewables connection needs to be based around high voltage systems. It doesn't. It needs to be based around high power capacity systems. And in changing that mindset, the whole energy system can leverage the benefits that can be accrued from superconductors, which can operate at lower voltages. So, I mean, there are challenges, technology challenges that we're addressing within the technology companies to bring down cost and to improve the efficacy of the technology. Where we need assistance from policymakers is in changing that mindset and then investing in that mindset. So investing in innovation and paving the way for demonstration projects to be delivered down the line, making sure we're not locked out because of a mindset that exists based on copper technology being seen as the way to deliver on decarbonization through renewables. It's not the case. We think there are new technologies such as superconducting cables, which will prove ultimately to be far more effective, efficient, and lower cost.
Thank you, Owen. Does anyone else have anything to add to this? Doug, yes, please go ahead.
Yes, I'd like to commend the policy of the German Bundesministerium as a good example, and I think also the European Union and the research sponsorship that have this long-term commitment that you start by funding and supporting innovation and R&D at the academic level, but then that you follow through the whole path through also the demonstration phase. Sometimes it can be difficult to finance and share the risk and the burden of bringing these new technologies to fruition, to actual benefit to the people. A lot of times it tends to be left out to the commercial interests, but there is a lot of risks when you go into this. So the more that the public institutions can share the burden of taking these risks to really go through this, you sometimes call it the valley of death. When something has been developed, is known, but before it can become a profitable solution for private companies to carry. That I think is quite important. And I think we see more and more of that, so that's very positive.
Thank you, Doug. And Norella, you would like to comment on that?
Yeah, I would like to add, so not directly NTOE, but the TSOs were involved, for example, in Best Path project, which I think it was mentioned on one of the slides in the beginning. So really for higher voltage, like I think it was 320 kV, that demonstrator. However, the project was closed some years ago, so I think 3 years ago. And I appreciate, Mario, that actually you mentioned that you will support this type of technology in in the previous call, I think this year, but also in the future. There is, I think, a need that this has a kind of portfolio of development, and it's a kind of how we can move faster than probably we moved until today, because yeah, personally, so I saw Best Path project. I was also a few years ago, I think in south of France, Cadarache, where they have the ITER, and they also look at superconductivity. So for the, yeah, there are applications in other sectors. So how we can actually develop this technology in a way faster, and then it's becoming faster also a reality. I think this is also a key message, and of course it might be related to different things, to yeah, existing systems, to supply chains, to monitoring systems which might need to be put in place to be deployed. But I think yeah, we would personally, I would like to see a little bit faster development, and afterwards, of course, deployment. Yeah, it's on the way.
Well, I don't think you will hear much objection to that on the part of our other panelists. Mario, please, would you like to respond to what Mirela has said?
Yes, indeed, it is true. We need to accelerate, but how? But on one side, I think the process has started, because we are realizing that we need these technologies lately. But I think the event is triggered. So there is more attention. We realize that the usual things cannot go on with this, the new challenges we have. So I think, and now we are pushed even more, because we need to be more quickly independent from energy dependent. So I think we will continue with this trend of accelerating deployment of new technologies, which is the only way to reach the energy targets, those energy targets. Yeah.
So maybe the question then to our other panelists: what could be done to speed up? What support could be? What would be useful for you to speed up? I think, Matthias, you also had some ideas about the challenges facing these companies.
Yes, I think that if I have a look at the attendees, I also see some from industry, and Doug already mentioned that this is awfully important to have a long run support on this technology. And as mentioned before, the demonstration projects all over the world are very good to support development of technology. That's a good point, but there's still a challenge. Where is the advantage for the early or first user? For the pioneers that first use this. We have to rely on Stadtwerke München in that case, because they really have a problem with that change in power density in Munich. So I don't see this. Very often we react only on changing environment, and we react fast and very good if you look to hydrogen and other technologies and batteries, but we react. Is there any chance to support users that we can act early enough on these application of this new technology? I don't see this at the moment.
Yeah, and if we look at, okay, the problems are occurring in the short term, but realistically, we can also see, looking ahead in 2050, what we are, the ambitions that we are trying to carry out. We will, these problems will come if we don't anticipate them. So how can we actually already now if we are planning for 2050, how can we already now make sure that these kinds of innovation are taken into account? I don't know if Mirela, you can say something more about that, or we have to wait for your event in October.
Yeah, I cannot say too much. I don't know if this is going to be further enhanced. It will be further enhanced by that time, but we see certain challenges also after, for example, I mentioned this best path project. So there were mentioned this, the name of the companies actually which provided solutions, so the European companies. However, there is also a need to accompany the development of the technology by probably additional measures. So of course, reduction of the cost, this is intrinsically related to the technology, but also how to say, the framework conditions in terms of monitoring of the system for the power system operators. It's important so that everything is secure, it's in place. Then the secure operation. So of course we tested these elements in the demonstration projects, but these have to be, if we want to upscale, so this has to be probably done at a larger scale, for example, for, I would think now, offshore application, and then interaction of, as you mentioned, Mario, so HVDC, multi-terminal, multi-vendor solutions, so how this can work together actually, and then the links towards AC systems.
Thank you very much for that, Norella. We have heard now about speeding up and what will be needed, but the question from the audience is, when will superconductors for the transmission grid be available commercially? Do our panelists have any thoughts on that?
I can jump in there again. So I've outlined Supernode's roadmap to date, and the medium-term milestone for us is 2025 to deliver a TRL6, so Technology Readiness Level 6 prototype, which will validate our key functionality in that. Beyond that, then we're planning actively now for demonstration projects through 2027, 2028. So these would be akin to the Opacity Project, so a TRL7 project. And ultimately then we're targeting commercial availability of our products beyond 2030, so from 2030 onwards.
Thank you, Owen, on that for that.
Yeah.
Doug, you want to respond to this question as well, or a different question? Okay.
That we're a systems and the product supplier, and we're aiming for these early niches that we perceive of urban congestion and maybe a little bit shorter distances of 1 to 20 kilometers. Now following our installation of a demo in Munich in 2023, it will take us probably in 2024 to prepare the commercial rollout. And then by 2025, these first products at the high voltage level should be available then, not at the highest voltages, but at the starting voltages of 110, 130 kilovolt. And for these short and intermediate distances.
Mike, go ahead.
Yeah, in partnership with Nexans, AMSC demonstrated 138 kV in a project in Long Island, New York in 2012, I believe, or 2010. So we are currently working with customers on projects in that voltage range and similar voltage ranges on a commercial basis. Also in Korea, there's 154 kV has been installed and demonstrated. So the transmission voltages, at least as Dag mentions, on the lower end of the transmission level voltages, which when you're talking about 3,000 or 4,000 amps in a single cable, is similar power levels as even 500 kV projects that's already commercially available today.
Very good, thank you. And another question from the audience. Does anyone know if there are companies working on developing switchgear to distribute these high currents into a conventional distribution system?
Dag,
I can jump in. Sorry, do you want to take that, Mike?
Sure. So today, 3,000 amp equipment is widely available. The vast majority of utilities use 3,000 amp equipment. 4,000 amp equipment is a little less commonly used, but is certainly commercially available. And then once you start getting into gas insulated installations, 5,000 amp equipment is available today. Above the currents above that level, probably start to get into the all of your eggs in one basket kind of problem. So you start to think about splitting things up at currents above those kinds of numbers. But in general, I would say the equipment that's currently commercially available is sufficient to do the vast majority of what we're trying to do.
Well, that's
I'd reiterate that. So we're working with the big equipment OEMs, and what they see in their equipment is an evolution rather than a revolution, which will be able to accommodate the new paradigm, which will be lower voltage and higher currents. I guess that they recognize that there is significant system benefit to be gained in going down that route, such as the advantage that's available at lower voltage in terms of size and cost.
We are already unfortunately at the end of our time because now the questions are really starting to roll in now that we've gotten everybody thinking. We have one question that I would still like to take on hydrogen. I know that Matthias also was interested in saying a few words on this, whether there would be a synergy between these two technologies in the near future. But to the rest, also, if there's any final words that you would like to share before our participants check out. Yeah. Any closing statements?
With respect to cables, I just want to mention that in Germany, a TSO needs a so-called pre-qualification test to show that the technology is mature enough. Yeah, this is nicely shown with the 525 kilovolt DC cable, conventional cable, that was done in 2018. Yeah, so this is maybe specific for Germany, but you cannot apply a new technology without that pre-qualification. And then the Superlink project in Munich is something like that. Yeah, it's a pre-qualification for the Stadtwerke Munich. And this would take 3 years, and then you can do it. You can really go to the longer length. In the meantime, develop some critical technology like longer length cooling, for example. Yeah. And what we have now, as you mentioned, hydrogen, we expect that some part of the hydrogen is liquid, yeah, because customers ask for it. We see this in trains or other applications. In clean aviation program of the European Commission, hydrogen plays also a big role. Yeah? And in this combination at 20 Kelvin anyway, superconductivity fits perfectly. Yeah? So we should not leave the hydrogen guys alone. Yeah? We should support them and think that some part is liquid, I'm sure. Yeah? And this is because of the highest energy density that you have. Yeah? The liquid hydrogen, you have the highest energy density of hydrogen, and then you have 20K, and that's what we should keep together. We try to do this in aviation projects, but it's rather difficult at the moment for a strategy, a general strategy, because hydrogen strategy goes in that way and superconductivity in that way, and in some part we have to merge. And thank you again for this wonderful seminar.
Thank you. Any last final, I see Mike has his hand up. Any last final words? I think then we really need to close the session.
Yeah, I would reiterate that the hydrogen can be used as a coolant to keep the superconductors cold, and you can have then systems that can deliver both hydrogen and electricity in the same pipe, and that's a concept that people have thought about for some time, but does need some more research and development. And then I would just mention to any the policymakers on the call that when we're trying to decarbonize our grid, not only does that mean that we're going to need more infrastructure in our cities in order to bring this extra power into the systems to run EVs and space heating, but that power will need to be more reliable. And conventional technologies is going to make it very, very difficult to do this with copper and aluminum cables. Technologies like superconductors are going to be absolutely critical to realize the things that we want to do.
Okay, thank you, Mike. Mario, can I leave the final word to Mario?
Yeah. Yeah, I know, I understand we are at the end, but just so three things I had in mind, some questions, but just to think about. One is I mentioned low temperature superconductor. If it is needed, what would be the benefits? If it's linked with hydrogen, maybe we've been discussing. The other thing is the cooling station, repeater cooling stations. If we think about the application in offshore, how do we deal with this issue? And this is a research. Do we have superconductors at room temperature? What is the state of development? Okay, this is
this is a
question.
no. Well, this is an open invitation, Mario. Anytime that you have questions, we will be happy to have any exchanges on this. So thank you very much to our panelists for joining us here today. Any questions that we didn't get to, please feel free to send me an email, and we will be happy to get to them at a later point. And thanks to our panelists, thanks to our audience, and have a nice rest of your day. Thank you.
Thank you.
Thanks, guys.
Bye. Thank you.
Thank you very much. Bye.